A single electron can strike a detector as one tiny point, one localized event, one mark that seems to say, here. But send electrons through two narrow openings one at a time and let the marks accumulate, and the pattern slowly refuses the simplest explanation. It does not become two ordinary piles behind the two openings. It becomes a set of bright and dark bands, the signature of interference, as if something wave-like passed through both routes before each electron arrived as a single dot. Ordinary intuition expects a small object to choose one path, even if we do not know which one. A grain of dust does not spread through two slits and later decide where it was. A pebble does not interfere with a path it did not take. If that simple picture were complete, the detector should record two blurred clusters, and the missing bands should stay missing forever. The interference would have no physical source. The phase relationships in the mathematics would be decoration, not measurement. But experiments do not let the simple picture survive. The quantum description begins not with a hidden little projectile waiting to be found, but with probability amplitudes, mathematical quantities that can reinforce or cancel one another before they become probabilities. When a measurement leaves path information behind, the interference disappears. When no path information exists, the bands return. The first wound in ordinary reality is not that particles are small. It is that nature seems to care not only what happens, but what can be physically known. This is not a story about human minds commanding matter. It is stranger and more disciplined than that. The crucial event is not a gaze. It is an interaction. A detector clicks, a photon scatters, an atom in a device changes state. A trace is left in the world. At that point, a possible path is no longer just part of a calculation. It has touched something larger. And that touch is where the trouble begins. In everyday life, the world does not behave like a set of interfering possibilities. A room at night is dark or lit. A glass of water sits in one place. A message on a phone has either arrived or it has not. When a hand moves toward a switch, the next second may feel open, but after the motion is complete, memory does not keep several incompatible rooms alive. There is one click, one change in brightness, one version of the room that continues. This single-line feeling is so natural that it becomes invisible. We wake into a world already arranged as facts. The door is open or closed. The key is in the lock or missing from it. The floor pushes back against the feet. Even uncertainty feels ordinary, because it usually means only that some fact is hidden from us. If you do not know whether a coin landed heads or tails, you assume it landed one way. Your ignorance is not a physical fog around the coin. It is only a limit in your information. Classical physics gave this instinct a powerful structure. In the familiar world of stones, planets, pendulums, wheels, tides, and falling rain, objects have positions, speeds, and forces acting on them. With enough information, at least in ideal cases, their motion can be calculated. A thrown object follows a path. A planet bends through space according to gravity. A compass needle settles because a magnetic field exerts a torque. The world looks complex, but not undecided. That classical picture is not a mistake. It works with astonishing reliability across the scales where human life happens. Buildings stand because atoms in solids form stable arrangements. Engines run because gases expand, fuel burns, and pressure pushes pistons. Bridges, satellites, clocks, lenses, aircraft, medical scanners, and electrical grids all depend on physical laws that treat many objects as if their properties were sharply defined. The ordinary world has edges. It has tracks. It has records. Yet the success of that picture hides a condition. It works where quantum delicacy has already been buried under scale, heat, noise, and constant interaction. A cup does not drift across a room in a visible superposition of locations because the cup is not an isolated quantum toy. It is a warm object entangled with air molecules, thermal radiation, vibrations, sound, and every surface it touches. Its position is being copied into the environment all the time, long before any person thinks to look. At the microscopic level, the older language begins to fail. An electron is not well described as a little bead carrying a complete private list of properties. A photon is not simply a tiny pellet of light that always has a definite path waiting behind it. Quantum mechanics uses a different object, the state. That state can contain more than one possible outcome for a future measurement, not as a poetic symbol, but as a precise mathematical structure. The word superposition often carries more drama than clarity. It does not mean that anything imaginable happens. It means that a quantum system can be described as a combination of states that would, if measured in a certain way, produce different outcomes. An atom may be in a superposition of energy states. A spin may be arranged so that measuring along one axis can give more than one possible result. A photon may be described by amplitudes associated with different paths. The crucial difference is that these possibilities can interfere. Ordinary possibilities do not do that. If a lost ring is either in a drawer or in a coat pocket, the two options do not cancel one another. They are just alternatives in your mind. But in quantum mechanics, the amplitudes connected to alternatives can have phases. When amplitudes meet, they can add. They can also subtract. This is why the final pattern on a detector can have places where particles often arrive and places where they almost never arrive, even though both places seemed reachable by ordinary reasoning. A probability amplitude is not itself a probability. That distinction matters. A probability is a number you can use directly. A 20% chance, a 50% chance, a near certainty. An amplitude is more like an instruction before the final number is made. It has size, but it also has phase, a relationship that lets it combine with other amplitudes. Only after the amplitudes are combined do we calculate probabilities that correspond to actual measurement results. This is why quantum mechanics can sound vague while being mathematically severe. The images become difficult, but the predictions are strict. If the experimental arrangement is known, the theory tells us how to calculate the distribution of outcomes. It does not usually say where one individual electron will land. It says how many electrons, after many repetitions, should land in different regions of the detector. In the pattern of many events, the hidden structure appears. The double-slit experiment is powerful because it compresses this entire conflict into one simple arrangement. A source emits particles. A barrier has two narrow openings. A screen or detector waits behind it. The drawing is almost childlike. The consequence is not. If ordinary particles were being fired through the two openings, each particle would pass through one slit or the other. The screen would collect impacts in two broad regions, softened by scattering and geometry. If a classical wave were sent toward the barrier, it would pass through both slits, spread out, overlap with itself, and form interference. Where wave peaks met peaks, the wave would strengthen. Where peaks met troughs, it would weaken. The screen would show alternating bands. Quantum objects arrive like particles, but distribute like something that has interfered. When electrons are sent one at a time, each detection is local. There is no half electron smeared visibly across the screen. The instrument records one impact, then another, then another. At first, the dots look random, almost meaningless, but as thousands or millions accumulate, the bands emerge. The quiet violence of the experiment lies in that slow emergence. Each electron seems to arrive alone. It is not bumping into a crowd of other electrons on the way through, yet the final distribution follows the rule for interfering amplitudes associated with both slits. If each electron merely had a secret path in the ordinary sense, and if our ignorance were the whole story, the interference pattern should not be there. The dots would still be dots, but their long-term map would be different. The experiment does not force one simple picture onto the mind. That is part of its strength. It does not say that the electron is literally a tiny water wave. It does not say that it is a classical pellet wearing a disguise. It shows that neither familiar image is enough. The electron is detected as a localized event, but the probabilities governing that event come from amplitudes that can combine across alternatives. Then the apparatus can be changed in one precise way. Add a mechanism that reveals which slit the particle passed through. It might be a detector near one opening, or a scattering interaction, or some physical mark that makes the two paths distinguishable. Once path information exists in the apparatus or the environment, the interference pattern disappears. The detector no longer builds alternating bands. It begins to build the kind of distribution expected from particles taking one route or the other. This is the point where careless language becomes dangerous. It is tempting to say the electron knows it is being watched. It is tempting to imagine nature becoming shy under inspection. But nothing in the experiment requires that. What matters is not embarrassment, attention, or consciousness. What matters is whether the alternatives remain capable of interfering. Path information changes the quantum state because the particle becomes correlated with something else. The two alternatives no longer remain clean parts of a single coherent description. The path mark is not a label attached after the fact. It is a physical change. A detector must end in different states depending on which path occurred. A photon scattered from the particle carries information away. A material surface absorbs energy in one place rather than another. The environment becomes slightly different depending on the route. Once that happens, the alternatives are no longer arranged as pure possibilities that can meet and cancel in the same way. In ordinary life, information feels weightless. A fact can be written in a notebook, remembered by a person, stored on a chip or ignored. But in physics, information has a body. It is carried by physical states. A magnetic domain points one way instead of another. An electric charge moves. A molecule changes shape. A photon heads outward with a slightly altered direction. A measurement result is not a ghostly statement. It is a pattern in matter and energy. This gives measurement its real force. To measure a quantum system, something must interact with it strongly enough, or specifically enough, to correlate one possible outcome with a distinct physical record. That interaction changes the combined system. If an electron's position is measured, the electron has not merely been seen from a distance. It has participated in an event with a detector. If a photon's path is recorded, the photon has not merely confessed its route. Its route has become entangled with another physical object. The word observer therefore needs to be handled carefully. In common speech, an observer is a person with eyes and attention. In quantum physics, the effective observer may be a detector, a photographic plate, a cloud of gas, a stray photon, a thermal bath, or the wider environment. Human awareness can come later, after the result has already been amplified, stored, copied, and stabilized. The world does not wait for a mind before every interaction has consequences. That does not make the problem smaller, it makes it sharper. If measurement is just physical interaction, then the old boundary between quantum possibility and classical fact cannot be drawn at the human eye. It must be drawn, if it can be drawn at all, somewhere in the chain of physical coupling: system, detector, amplifier, environment, record, memory. And each link in that chain is made of atoms that, under the same theory, are quantum objects too. A particle approaches a detector. The particle is described by a state with several possible outcomes. The detector is built from atoms, electrons, electromagnetic fields, and moving charges. If the detector records one result, its internal state changes. If it records another, it changes differently. But if quantum mechanics applies to both the particle and the detector, then before a final outcome is selected, the combined description can appear to contain correlations between multiple possible particle results and multiple possible detector states. This is where the measurement problem begins to take its real form. It is not merely the question of why a particle behaves strangely, it is the question of how a theory built from superpositions gives rise to a world of single records. The equations describe smooth evolution of quantum states. Measurements produce definite outcomes. The formalism tells us how to calculate the probabilities of those outcomes with remarkable success. But the transition from a spread of amplitudes to one experienced result is not as simple as the word measurement makes it sound. Historically, one way to handle this was to speak of collapse. Before measurement, the wave function contains several possible results. During measurement, it collapses into one. Afterward, the system is described by the state corresponding to the observed outcome. This language is practical. It helps physicists calculate what happens in laboratories. It matches the fact that when a detector clicks, it clicks in one way, not in all ways at once. But collapse is not a small word. If it is a real physical process, what triggers it? How fast does it happen? Does it occur when a microscopic system touches a detector, when the detector amplifies the signal, when information enters the environment, or when someone reads the display? If it is not a physical process, but only an update of our description after we learn the result, then why does the world itself appear to contain only one result, not merely our knowledge of it? Different interpretations answer these questions differently. Some treat collapse as a genuine feature of nature. Some treat it as a rule for updating information. Some attempt to remove collapse entirely and keep only continuous quantum evolution. The experiments in many standard cases do not immediately choose between these pictures because they can lead to the same observable statistics. The disagreement is not usually over the success of the calculations. It is over what kind of world those calculations are describing. This is a rare kind of scientific unease. It is not caused by a failed prediction. Quantum mechanics is among the most successful theories ever built. It explains atomic spectra, chemical bonds, semiconductors, lasers, magnetic resonance, superconductivity, and the microscopic structure behind much of modern technology. The unease comes from the opposite direction. The theory works so well that its strange language cannot be dismissed as temporary confusion. The patterns are real. The calculations bite into the world. A laboratory detector does not care whether its philosophical interpretation is elegant. It records events. A photomultiplier amplifies a faint signal into an electrical pulse. A superconducting device registers a change in current. A CCD sensor stores charge in a pixel. A cloud chamber reveals tracks as vapor condenses along paths left by ionizing particles. Each instrument turns microscopic interactions into macroscopic marks. The marks are definite enough to be photographed, counted, compared and archived. That definiteness is exactly what needs explanation. At the level of the recorded event, the world seems classical again. The detector has a value, the screen has a dot, the lab notebook has a number. A second physicist can come later and read the same entry. The result has become part of a shared environment. It is no longer an abstract amplitude waiting in a calculation. It is a fact with consequences. Yet the path to that fact runs through a theory in which alternatives can coexist in the state and affect one another through interference. The ordinary world, therefore, cannot simply be assumed as the starting point. It has to be recovered. Somewhere between the isolated quantum system and the durable laboratory record, the fragile ability of alternatives to interfere becomes unavailable. The world narrows, at least from the inside, into one history. The narrowing is not always abrupt in the equations. A quantum system can gradually lose coherence as it interacts with its surroundings. Coherence means that the different parts of a superposition maintain the precise phase relationships required for interference. When those relationships remain protected, the system can display unmistakably quantum behavior. When the relationships are dispersed into the environment, interference between the alternatives becomes effectively inaccessible. Even without naming the full process yet, the physical picture is already visible. A tiny isolated system can be kept delicate. A large warm object cannot. The large object is constantly struck by air molecules, emitting and absorbing thermal radiation, vibrating internally, coupling to surfaces, and spreading information about its state into countless degrees of freedom. Every contact is a small leak. Every leak carries a trace. The more traces spread, the harder it becomes for the original alternatives to meet again. This is why the familiar world feels so stable. It is not because quantum mechanics stops existing at the edge of a visible object. It is because visible objects are almost never isolated in the way quantum interference requires. They are open systems. They are continuously monitored by the environment, not by minds, but by collisions, fields, radiation, heat, and contact. The environment is not a person looking at the world. It is the world touching itself. Still, saying that the environment destroys interference for practical purposes does not yet explain why one outcome is experienced. It explains why alternatives stop interfering in any usable way. It explains why macroscopic records behave classically. It explains why a detector pointer does not visibly hover between incompatible readings. But depending on interpretation, it may not by itself say whether the other mathematical components vanish, become inaccessible, or were never physical in the same sense. Here the mystery has moved. It no longer sits only in the microscopic object, it now sits in the act of becoming a fact. An electron at a double slit is strange, but a detector recording a single outcome is stranger, because the detector is made from the same quantum ingredients. The question is no longer simply, which slit did the particle pass through? The question becomes, how does any question receive only one answer? The everyday world depends on that answer. Without the emergence of stable records, memory would not behave like memory. Instruments would not behave like instruments. The past would not be written in durable traces. A thermometer could not be trusted to show one temperature. A photograph could not preserve one arrangement of light. A computer bit could not remain readable. A body could not navigate a world in which macroscopic alternatives kept interfering with one another. The fact that this does not happen is not trivial. It is a physical achievement performed continuously by scale and interaction. The room stays a room because information about its surfaces, objects, temperature, and illumination is redundantly scattered into the air and light around it. A lamp is not merely lit or unlit for a person. Its state is impressed into photons, warmed materials, electrical currents, shadows, and reflections. Reality, at human scale, is heavily recorded. This helps explain why quantum weirdness is so hard to see directly. It must be protected from the very thing that makes ordinary reality reliable. To see interference, physicists isolate systems, reduce noise, control fields, cool devices, filter stray radiation, and prevent information from leaking away. They create conditions in which alternatives remain capable of combining. The experiment is not just a window into strangeness, it is a shelter built around fragility. The shelter can be extraordinarily precise. Single photons can be guided through optical paths. Ions can be held in electromagnetic traps. Electrons can be confined in carefully engineered structures. Superconducting circuits can be cooled to temperatures near absolute zero, so that collective electrical states behave quantum mechanically. In each case, the goal is not to make nature strange. It is to stop the environment from immediately making it ordinary. This reversal matters. Quantum behavior is not an exotic decoration added to the world. It is the underlying rule that must be protected when we want to observe it cleanly. Classical behavior is what emerges when that rule is applied to systems that are large, warm, noisy, and open. The familiar world is not fake, and it is not an illusion. It is a remarkably stable regime produced by conditions that erase interference between alternatives faster than ordinary perception can follow. The speed can be astonishing. For macroscopic objects in normal environments, the loss of observable coherence can happen on timescales so short that they have no human analogy. The object does not need to wait for someone to open a door or check a gauge. Its possible macroscopic states become entangled with so many environmental details that the interference terms in the effective description become negligible almost immediately. The world has already chosen a practical language before awareness arrives. And yet, the word chosen must be used carefully. In one interpretation, a real collapse selects a single outcome. In another, the apparent selection is tied to the branching structure of the quantum state. In another, the wave function may represent knowledge rather than a direct physical object. The same measured facts can be read through different conceptual lenses. What cannot be avoided is the operational fact. When the apparatus is read, one outcome appears. This one outcome structure is the deep familiarity at the center of the problem. It is so close to us that it rarely feels like a mystery. A camera captures one image. A Geiger counter produces one sequence of clicks. A person remembers one version of a conversation. But quantum mechanics asks why the underlying description, which can include multiple possible outcomes before measurement, gives rise to that singularity so consistently. To feel the pressure of the question, imagine a quiet laboratory after midnight. The room is mostly dark. A shielded apparatus sits on an optical bench. Inside, a source emits one quantum object at a time. No one needs to be staring at it. The equipment is aligned, cooled, isolated and silent except for the small electronics that record each event. On the detector, a pattern begins as scattered points. Later, the structure appears. Nothing in a single dot reveals the rule behind it. A dot is too final. It arrives without explaining how it was chosen. Only the accumulation speaks. The statistics tell us that the alternatives before measurement were not ordinary hidden facts. They carried phase, they interacted in the calculation, they shaped where future dots could appear. The single result is simple only after it has happened. Now add path detection. The apparatus gains a memory of which route was taken, the interference fades, the final pattern changes. The lesson is not that knowledge floats above physics, but that a record is a physical condition. The world behaves differently when alternatives leave distinguishable traces. To make a fact is to rearrange matter so that one alternative has a durable signature. This is where the familiar room and the quantum laboratory quietly meet. Your ordinary evening is full of durable signatures. The light switch has a position. The filament or diode has a state. The walls scatter photons according to the lamp's condition. Your eyes, nerves, and memory become correlated with the result. The room does not remain in an observable mixture of lit and dark because the distinction has exploded into the environment. It has become too widely recorded to behave as a protected quantum alternative. But this explanation also sharpens a dangerous-sounding question into a scientific one. If every measurement is an interaction, and every interaction is made of quantum systems, where exactly does a measurement begin? A single atom can hold a superposition. A molecule can, under careful conditions, show quantum interference. Engineered devices larger than atoms can be placed into controlled quantum states. The boundary is not painted on nature as a simple line between small and large. Size matters, but not alone. Isolation matters. Temperature matters. The number of internal degrees of freedom matters. The strength of coupling to the environment matters. The availability of information matters. A microscopic system can become classical-like quickly if it leaks information. A larger artificial system can remain quantum-like if it is protected with extreme care. The boundary is not a wall, it is a competition between coherence and entanglement with the surroundings. For late-night intuition, this is almost the opposite of common sense. We think the large world is naturally definite because it is large. Quantum theory says the large world is definite because it cannot keep secrets. Its alternatives are exposed. They are copied into air, light, heat, and matter. They lose the protected relationships that would allow interference. The ordinary world is not quiet at all. It is overflowing with uncontrolled measurement-like interactions. This is why the old image of a conscious observer misses the mechanism. A mind may read a result, interpret it, remember it, and attach meaning to it. But the physical stabilization of that result begins earlier. By the time awareness enters, the record may already be multiplied into countless correlations. The detector has changed, the electronics have changed, the surrounding electromagnetic field has changed, the information has spread. The human observer is not irrelevant in the human sense. Science is done by people, and experience is where results become known to us. But the electron does not need a human face in order for interference to be lost. A single uncontrolled interaction can be enough to mark a path. A warm environment can mark it overwhelmingly. Consciousness is not required to make the detector a physical participant in the process. That distinction protects the mystery from exaggeration. Quantum mechanics does not give permission to say that thought directly creates external facts. It does not show that attention alone bends particles into outcomes. The real mystery is more exacting. The formalism treats measurement in a special way, yet measurements are carried out by physical systems that should themselves obey the formalism. The problem is not mystical power, it is consistency. And consistency is what makes the next step unavoidable. If an atom can be in a superposition, and if a detector can become correlated with the atom, then what happens when the detector is connected to something much larger? How far can the quantum description be extended before ordinary language breaks under it? If the chain continues from atom to device, from device to room, from room to observer, Does the theory produce one world by itself, or does something extra enter? The first physicists who faced this question did not treat it as entertainment. They knew the mathematics worked. They also knew that if it were applied too literally to familiar objects, it seemed to produce descriptions that sounded absurd. A microscopic uncertainty could, in principle, be amplified into a macroscopic difference. A tiny quantum event could determine whether a large apparatus took one path or another. The small and the large could not be kept separate by intuition alone. The most famous thought experiment built around this pressure places a living creature in a sealed box, not because the cruelty is the point, but because the contrast is impossible to ignore. A quantum event such as the decay of an atomic nucleus is connected to a mechanism with a macroscopic consequence. If the nucleus decays, one outcome follows. If it does not, another follows. The quantum event is small, the consequence is large. The question is whether the superposition travels upward through the chain. No one needs to imagine actual laboratories filled with impossible cats. The purpose of the scenario is to expose the tension. Quantum theory can describe a nucleus in a state that, before measurement, includes decayed and undecayed possibilities. A mechanism can be arranged so that those possibilities become linked to visibly different outcomes. If the theory is applied without a clear rule for when collapse occurs, the entire system seems to inherit the ambiguity. But our experience does not deliver ambiguous cats, ambiguous instruments, or ambiguous memories. It delivers one result. Here the problem expands. The double slit shows that quantum possibilities are not merely ignorance. Measurement shows that information is physical. The detector shows that a record is made by interaction, not by a magical gaze. And the sealed box thought experiment asks whether the same rules that govern an atom can be carried all the way into the world of warm bodies, irreversible traces, and ordinary facts. If measurement is only a physical touch, how large must the touch become before a possibility turns into the one world we remember? The sealed room is not important because of the animal inside it. It is important because of the chain. A nucleus may decay or not decay. A detector may register that decay or remain silent. A mechanism may move or stay still. A large system may end in one condition or another. The thought experiment forces the quantum event to climb upward, link by link, until the difference is no longer microscopic. That climb is what makes the image uncomfortable. If the nucleus alone is described by a superposition of decayed and undecayed possibilities, and if the detector becomes correlated with that nucleus, then the detector's state seems to enter the same, larger description. If the detector controls a macroscopic mechanism, the mechanism becomes part of the chain. If the sealed room contains an organism whose condition depends on the mechanism, the organism is drawn into the question. The difficulty is not that anyone expects a real cat to float visibly between life and death. The difficulty is that the theory does not provide an obvious ordinary place to stop. In daily language, the stopping point feels obvious. Small things may be quantum, large things are real. But that division is too rough to be a law. Large things are made of small things. Detectors are made of atoms. Living tissue is made of molecules. A laboratory apparatus is not outside physics simply because it is large enough to see. If the quantum description applies to the ingredients, it is not enough to say that the final object is too familiar to be included. Schrödinger's purpose was not to decorate quantum mechanics with absurdity. The cat was a pressure test. It showed that the language of superposition, harmless enough when applied to a microscopic system, becomes deeply strained when a microscopic uncertainty is amplified into a macroscopic consequence. A radioactive nucleus is not a cat, but a mechanism can connect them. And once the connection exists, the measurement problem becomes a problem about the whole chain of physical correlation. The ordinary answer says, when we open the room, we find one result. The cat is alive or not. The device is triggered or not. The record says one thing. This is how the world appears, and no serious interpretation can ignore it. But the question is not whether the final experience is definite. The question is how definiteness enters the description. Does the wave function truly collapse? Does only one outcome physically remain? Or does the larger quantum state keep all allowed outcomes in a form that can no longer interfere? This is where the word collapse begins to lose its simplicity. In calculations, collapse is clean. You have a set of probabilities before measurement. You measure. You update the state to match the result. But as a physical story, collapse asks for a trigger. It asks where, when, and by what mechanism the smooth quantum evolution stops, and a single outcome is selected. If the answer is simply at measurement, then measurement itself has become the unexplained boundary. One response is to make collapse real. In collapse theories, the wave function does not merely appear to reduce because someone learned something. It undergoes an actual physical change. Such ideas try to modify or complete quantum mechanics by adding rules that turn superpositions into definite outcomes, especially for large systems. The advantage is directness. One world remains because the others are removed by a process in nature. The cost is that the process must be specified precisely enough to fit experiments that already confirm quantum behavior with extraordinary accuracy. Another response is more austere. It refuses to add a collapse rule at all. It says the quantum state always evolves according to the same smooth equation, even during measurement. The detector, the environment, and the observer are not outside the state. They become part of it. The price of this move is not mathematical inconsistency. The price is conceptual scale. If the wave function never collapses, then all outcomes allowed by the quantum state may continue in a larger structure, separated not by distance, but by their loss of mutual interference. Hugh Everett III took that path in the mid-20th century. His proposal was not built from a fantasy of alternate lives. It came from a technical discomfort with giving measurement a special exception. Everett asked what happens if the quantum equations are taken seriously even when a measurement is performed. A system begins in a superposition. An apparatus interacts with it. Instead of selecting one term and deleting the others, the combined state becomes a superposition of correlated outcomes. This system result with this apparatus reading, and that system result with that apparatus reading. From inside one correlation, the world appears singular. A detector reads one value. A person remembers one value. The laboratory record is consistent with that value. But in the full description, according to the many worlds interpretation, the other allowed outcomes are not destroyed. They continue as other branches of the quantum state, each with its own internally consistent record. The word worlds is dramatic, but the underlying claim is more technical. Measurement produces branching correlations rather than collapse. A branch is not a place behind the wall. It is not a hidden room in space. It is not a neighbouring universe that could be reached by a tunnel, a signal, or a sufficiently clever machine. It is a component of the quantum state that has become effectively independent from other components, because interference between them has been lost. The separation is not geographical, it is structural. It lies in the way the system, apparatus, observer, and environment have become correlated. This is why the popular image of many worlds can both help and mislead. It helps because it captures the unsettling idea that the alternatives may not simply vanish. It misleads because it turns a mathematical structure into a landscape of cinematic copies. The interpretation does not show that every ordinary hesitation creates a new visible universe in the naive sense. It does not prove that every personal road, every sentence left unsaid, every small human regret exists as a nearby scene waiting somewhere. The more careful claim is narrower. Quantum measurements may branch the universal state into non-interfering components. Even that narrower claim is enough to put pressure on intuition. In the collapse picture, one outcome becomes actual and the others disappear from the physical story. In the Everett picture, the equation does not choose. It correlates. Each observer inside a branch finds a single result because that observer has become part of the correlation. The experience of singularity is real from within the branch, but the full state is wider than any one record inside it. This produces a quiet reversal. The question is no longer why there are many possibilities before measurement. The question is why any observer experiences only one. In the many worlds view, the answer is that observation itself is branch relative. A version of the observer who sees result A is physically correlated with the apparatus reading A. Another version, in another branch, is correlated with result B. neither sees a blur, because each memory is tied to a definite record within its own branch. The idea sounds extravagant because it multiplies outcomes, but it is also, in another way, conservative. It avoids adding a special collapse event. It keeps the quantum evolution smooth. It treats measuring devices and observers as physical systems rather than exceptions. Its boldness comes not from changing the equations, but from accepting their full consequence. The mathematics remains compact. The implied ontology becomes difficult to picture. That difficulty is not a weakness by itself. Many successful theories have forced ordinary imagination to surrender its first draft. Relativity made time depend on motion and gravity. Quantum mechanics made properties depend on measurement context in ways classical intuition did not expect. But a difficult picture still needs discipline. Many worlds is an interpretation of the formalism, not a photograph of hidden corridors. It does not let us communicate with other branches. It does not allow someone to harvest information from outcomes they did not observe. It does not turn fantasy into engineering. Its central problem is probability. If all allowed outcomes occur in some branch, why should one outcome feel more likely than another? In ordinary probability, uncertainty makes sense because only one event will happen, and we do not know which. But if every outcome occurs somewhere in the total wave function, probability must be understood differently. It may be tied to the weights of branches, to the squared amplitudes that already govern quantum statistics. But explaining why those weights match experienced likelihood remains one of the interpretation's demanding tasks. There is also the question of counting. In a simple story, branches sound like separate items, 1, 2, 3, but the quantum state is not usually divided into clean, countable worlds like books on a shelf. Branching is often approximate, continuous, and tied to interactions with the environment. The number of branches is not always well defined in a simple way. What matters physically is not a neat census, but the emergence of effectively independent histories that no longer interfere. This is where decoherence becomes essential. Without decoherence, many worlds would be only a vast claim about possibilities. With decoherence, the claim gains a mechanism for why those possibilities stop mixing in the world we observe. Decoherence describes how a quantum system loses observable interference between parts of its state when information about those parts becomes distributed into the environment. It is not a philosophical decoration added after the fact. It is a process that can be modelled, calculated, and tested in controlled systems. Imagine a quantum system prepared in a superposition of two states. For interference to be visible, the relation between those two states must remain clean. Their phases must stay coordinated. The alternatives must remain capable of being recombined. But if each alternative leaves a different mark on the environment, the situation changes. A molecule of air scatters differently. A photon carries away a slightly different direction or energy. A detector element shifts into a different microscopic configuration. The environment begins to carry which state information. Once that information spreads into many uncontrolled degrees of freedom, the original interference becomes effectively unavailable. The system alone no longer behaves as if its alternatives can neatly recombine. In the mathematical description used for the system by itself, the interference terms shrink or become inaccessible for all practical purposes. The environment has not necessarily destroyed the full quantum state in every interpretation. It has entangled itself with the alternatives so thoroughly that the alternatives no longer act like parts of one coherent possibility in the reduced description. A useful comparison is not a collapsing building, but a whisper entering a forest. At the source, the sound has structure. It has timing, pitch, and phase. But as it scatters from leaves, trunks, uneven ground, and moving air, its structure is redistributed into countless tiny motions. The sound energy has not vanished into magic. It has become spread into the environment in a way that is practically impossible to reverse. Decoherence works with quantum information rather than ordinary sound. But the loss of accessible structure has a similar flavour. The difference is that quantum coherence is more exacting than sound. It requires phase relationships between alternatives. It can be destroyed by traces too small for human senses. A single scattered photon can carry enough information to make two paths distinguishable. A small thermal disturbance can couple a delicate system to outside degrees of freedom. A vibration in a material, a charge fluctuation, a stray electromagnetic field, or a microscopic defect can matter if it becomes correlated with the quantum state. This is why macroscopic superpositions are so hard to preserve. A large warm object has enormous internal complexity. Its atoms vibrate. Its surface exchanges photons with the room. Molecules collide with it. Heat flows through it. Every part is interacting with every other part and with the outside world. If two macroscopically different states were placed into a superposition, the environment would become correlated with the difference almost immediately. The relative phase information would be dispersed into a space of variables too vast to control. The sealed cat in that light is not isolated in the way a textbook state vector is isolated. A living organism is a storm of biochemical interactions. It breathes, radiates heat, absorbs and emits photons, circulates fluids, fires neurons, metabolizes molecules, and exchanges energy with its surroundings. Even in a sealed box, the cat is not quantum clean. Its different macroscopic conditions would imprint themselves into air, radiation, internal tissue states, and the device around it. Decoherence would make interference between those conditions unobservable with overwhelming speed. This does not fully solve the measurement problem in every interpretation. It does not by itself prove whether collapse happens or does not happen. It does not answer all questions about why a particular outcome is experienced, but it does explain why the world of large objects behaves classically. It explains why macroscopic alternatives do not produce visible interference. It explains why records become stable. It shows how the environment continually selects robust states by copying information about them outward. That copying is subtle, but powerful. A classical-looking fact is not merely present in one place. It is often redundantly recorded. The position of a dust grain is scattered into many photons. The shape of a key is reflected into light from many angles. The reading on an instrument influences electrical signals, heat patterns, memory cells, and human notes. Many observers can learn the same fact because the environment contains many copies of the relevant information. In this sense, objectivity is not just a philosophical agreement, it has a physical basis in redundant records. A quantum state protected from the environment is fragile because it does not yet have that kind of public existence. Its alternatives are not copied everywhere. They remain, in the ideal case, able to interfere. Once the information becomes widely shared, the system gains classical stability but loses quantum delicacy. The world becomes easier to agree on because it has become harder to reverse. This makes decoherence both a bridge and a boundary. It bridges quantum rules and classical experience by showing how one can emerge from the other under ordinary conditions. It also marks a boundary for technology. If we want to use quantum behavior, we must prevent the environment from doing what it naturally does. We must stop it from learning too much too soon. That requirement turns the abstract measurement problem into engineering. It is one thing to say that amplitudes can interfere. It is another to build a device in which they remain coherent long enough to perform a useful task. The laboratory must become a controlled silence around the quantum state. Temperature must fall, vibrations must be reduced, electromagnetic noise must be filtered, materials must be purified, pulses must be timed with precision. The machine must protect possibility without allowing it to dissolve into randomness. A quantum computer is built at exactly this edge. It is not a magical version of a classical computer. It does not simply try every answer in parallel and hand back the correct one. That image is easy to remember and usually wrong in the details. A quantum computer works by controlling amplitudes. It prepares qubits, evolves them through quantum gates, allows amplitudes associated with different computational paths to interfere, and then measures the system so that useful answers become more likely. A classical bit is definite in the computational sense. It is 0 or 1. Physically, it may be represented by a voltage, a charge, a magnetic state, or another stable configuration. a qubit can be placed in a superposition of the states labelled 0 and 1. But the power of the qubit is not that we read both values at once. When measured, the qubit yields one classical outcome. The useful work happens before measurement, while the amplitudes are still being shaped. The most important word is shaped. A quantum computation is not a cloud of possibilities left adrift. It is a controlled sequence of operations designed so that some amplitudes reinforce one another and others cancel. The wrong answers must be suppressed by interference. The useful outcomes must be amplified. If the device merely spread amplitude across a huge space and then measured, the result would often be no better than a complicated random draw. The algorithm has to choreograph cancellation. This makes the double slit a small ancestor of quantum computation. In the double slit experiment, there are two path amplitudes, and their interference shapes the pattern on a screen. In a quantum processor, the state may occupy an enormous mathematical space built from many qubits. The interference is not drawn as bright and dark bands on a wall, but it is still the working principle. The final measurement samples from a probability distribution sculpted by the quantum evolution. The scale grows quickly. 2 qubits require a state described by amplitudes for 4 basis states. 3 qubits require 8. 10 qubits require over 1,000. 50 qubits require more than a quadrillion basis amplitudes in the full mathematical description. That does not mean the machine stores ordinary classical numbers in all those slots in a directly readable way. It means the quantum state lives in a space whose structure classical intuition cannot easily flatten. The challenge is to make that structure do useful work before decoherence ruins it. Every extra qubit brings promise and danger together. The state space expands, giving algorithms more room for interference and entanglement. But each qubit is also another physical object that can leak information, another place where noise can enter, another channel through which the environment can learn something about the state. More qubits do not automatically mean a more powerful computer. They mean a more demanding fight against error. This is why quantum error correction is not an optional accessory. In ordinary computers, error correction protects bits from flips, noise, and imperfect hardware. In quantum computers, the task is harder because directly measuring a qubit can destroy the very superposition the computation needs. The information must be protected without simply looking at it in the classical way. Error correction spreads logical quantum information across many physical qubits and uses carefully designed measurements to detect certain errors without revealing the encoded quantum state itself. That sentence hides a remarkable constraint. To correct a quantum computer, the machine must learn what kind of error has happened without learning the answer too early. It must extract information about the noise, not the computation's fragile content. If it learns the wrong thing, it becomes a measurement device and collapses or decoheres the useful structure. Quantum error correction is therefore not just repair, it is controlled ignorance. The machine must know enough to survive, but not enough to destroy what it is protecting. Noise comes in several forms. A qubit can relax from one energy state toward another. Its phase can drift, damaging the interference relationships. Gates can be imperfect. Neighbouring qubits can couple when they should not. Control pulses can be slightly wrong. Materials can contain microscopic defects that act like unwanted environments. At the scale of a quantum processor, the boundary between computer and surrounding world is not a clean metal case. It is a battlefield of small couplings. This is why many quantum devices operate at temperatures close to absolute zero. Cooling reduces thermal noise. It quiets many unwanted excitations. In superconducting circuits, for example, extremely low temperatures allow collective electrical states to behave quantum mechanically with less disruption. Other platforms use trapped ions, neutral atoms, photons, spins in solid materials, or topological ideas that aim to protect information in more robust ways. Each platform has its own strengths, its own failure modes, and its own way of negotiating with decoherence. The engineering details differ, but the central demand is the same. Keep the quantum state coherent long enough, control it accurately enough, prevent the environment from stealing which path information from the computation, Then, at the end, measure in a way that turns the shaped amplitudes into a useful classical result. The entire machine lives between two opposing needs: isolate the state so it stays quantum, and control it so it actually computes. This is a deeper version of the measurement problem made practical. A qubit that is too isolated cannot be controlled or read. A qubit that is too connected loses coherence. The device must open and close its doors to the world with extreme precision. During computation, the quantum state must remain protected. During gates, it must respond to control. During readout, it must become a classical record. The machine has to decide physically when possibility is still useful and when it must become fact. The promise of quantum computing comes from problems whose structure matches that ability. Some quantum algorithms can factor large numbers more efficiently than known classical methods. Others can search or sample in ways that may offer speed-ups under specific conditions. Quantum simulation may become especially natural, because quantum systems are hard for classical computers to model precisely. A quantum machine can, in principle, use quantum behavior to study other quantum behavior. But the promise is not universal acceleration. A quantum computer will not make every task faster. It will not replace ordinary computers for writing text, streaming video, sorting simple files, or running everyday software. Its advantage appears only where the problem can be translated into operations that exploit superposition, entanglement, and interference. Without the right structure, the machine's quantum nature does not automatically help. The word entanglement enters here with weight. Entangled qubits cannot be fully described as independent pieces with their own separate states. Their correlations belong to the combined system. This is one reason quantum computation becomes difficult to simulate classically. The full state of many entangled qubits can contain relationships that are not reducible to a list of individual qubit properties. The machine's power, when it appears, comes from these carefully arranged correlations as much as from superposition alone. Entanglement also increases fragility. If the useful information is stored in correlations across many qubits, then damage to one part can spread through the logic of the computation. The processor is not a box of independent coins. It is a coordinated quantum object. Errors can disturb phases, correlations, and amplitudes in ways that do not resemble ordinary bit mistakes. Protecting the computation means protecting relationships. This brings the tension back with sharper edges. Quantum mechanics gives access to a wider mathematical state space, but the world constantly tries to turn delicate relationships into public records. In a double-slit experiment, which path information erases the interference pattern? In a quantum computer, leaked information erases the computation's advantage. In a macroscopic room, environmental records give us the stable classical world. The same mechanism that makes ordinary reality reliable also makes quantum advantage difficult. That is why decoherence is both enemy and teacher. It is the enemy because it destroys the coherence needed for controlled interference. It is the teacher because it reveals exactly what must be protected. It shows that quantum information is not just a number hidden inside a device. It is a physical relationship distributed through states, phases, and correlations. When that relationship leaks into the environment, the computation does not merely become messy. It loses the very structure that made it quantum. The popular phrase that a quantum computer computes in parallel universes tries to capture this strangeness, but it can obscure the mechanism. In the many worlds interpretation, one may describe different computational branches as components of a larger state, but the practical device still succeeds only by interference between amplitudes. If the branches were simply separate classical worlds that never interacted, they could not help one another find an answer. The power comes from the fact that before decoherence, the amplitudes can still combine. This is an important correction. The useful quantum computer is not a democracy of isolated universes voting on a result. It is a physical system in which alternatives remain coherent enough to affect one another. The wrong alternatives must cancel. The useful alternatives must add. The final measurement is not an all-knowing window into every path. It is a single classical outcome sampled from a distribution that the algorithm has tried to shape. So even when many worlds' language is used, it must be handled carefully. If branches have already decohered completely, they cannot be recombined in the ordinary way. For quantum computation, the machine needs coherent superposition, not merely many inaccessible histories. It needs alternatives that still retain the phase relationships required for interference. The moment the environment learns too much, the useful quantum parallelism becomes an ordinary mixture and the advantage evaporates. This is why the phrase built from possibility is almost exact, but only if possibility is understood physically. A qubit's possibility is not human indecision. It is not a mental openness. It is a controlled amplitude structure in a real device. The possibility must be prepared by fields, pulses, traps, circuits, or photons. It must be maintained against heat, noise, and unwanted measurement. It must be processed by operations that respect quantum rules. And it must finally be converted into one record. Every successful quantum operation is therefore a small act of balance. Too much exposure to the world and the state decoheres. Too much isolation and the state cannot be used. Too little control and the amplitudes do not interfere in the right way. Too much uncontrolled measurement and the computation ends before it has begun. The machine is not fighting nature in the crude sense. It is exploiting one layer of nature while suppressing another. This gives quantum technology a strange philosophical honesty. It cannot hide the measurement problem behind words. It has to build hardware at the boundary where measurement becomes real. If the theory's concepts were only metaphors, the devices would fail. If superposition were only ignorance, the algorithms would not work in the same way. If decoherence were only a philosophical worry, engineers would not need refrigerators, shielding, calibration, error correction, and careful isolation. The machine forces the abstractions to become physical. Yet the machine also refuses to answer every interpretive question. A quantum processor can demonstrate interference among many controlled states. It can show that quantum coherence is technologically useful. It can reveal how fragile quantum information is, but it does not decide by itself whether collapse is real or whether all branches persist. It operates within the formalism shared by several interpretations. It is evidence for quantum mechanics, not a simple verdict on the metaphysics of quantum mechanics. That restraint matters because the success of quantum technology can easily be turned into a story too large for the evidence. The existence of qubits does not prove that every life choice creates an accessible alternate world. The difficulty of measurement does not prove that consciousness selects reality. The strange behavior of amplitudes does not turn uncertainty into magic. The narrower truth is already strong enough. Physical systems can occupy states that are not classical alternatives. And controlling those states requires preventing the world from learning too much. In the quiet of a quantum laboratory, this truth becomes almost tactile. Metal cylinders and cables descend into cryogenic stages. Microwave pulses carry instructions into circuits colder than interstellar space. Lasers hold ions in place. Vacuum chambers protect atoms from stray collisions. Detectors wait at the end of the process, ready to turn a fragile state into a number. The apparatus may look solid and industrial, but its purpose is to protect something that can be spoiled by a trace. The fragility is not weakness. It is the condition that allows interference. A violin string must remain free enough to vibrate, but anchored enough to produce a note. A qubit must remain isolated enough to keep phase, but connected enough to be prepared, controlled, and read. Push too far in either direction, and the function disappears. The instrument becomes mute, or the quantum device becomes classical noise. There is a deep continuity between the sealed room, the double slit, and the processor. In each case, the question is how possibility becomes record. At the double slit, path information changes the pattern. In the sealed room, a microscopic event threatens to scale into a macroscopic contradiction. In the processor, the same fragile superposition must be preserved long enough to calculate, then deliberately sacrificed to measurement. The problem is not confined to interpretation. It has become an engineering constraint. That constraint brings the discussion down from cosmic-sounding branches into matter. The surface of a chip can host defects that absorb energy. A control line can introduce noise. A trapped ion can be disturbed by a fluctuating electric field. A photon can be lost. A qubit can keep its state just long enough to be useful, or just short enough to ruin the computation. The difference between success and failure may lie in events far below ordinary perception. The more precise the machines become, the more clearly they reveal that the classical world is not the default background against which quantum strangeness appears. The classical world is what happens when coherence is not protected. Quantum technology is the art of delaying that ordinary fate. It keeps the system from becoming too public too soon. It allows the mathematics of amplitudes to work before the final record is made. And still, the record must be made. A quantum computer that never outputs a classical result would not be a useful computer. A measurement must eventually occur. The final state must be sampled. A bit string appears. The laboratory receives one outcome, not a visible cloud of all possible answers. The quantum advantage, if achieved, hides in the probability distribution that produced that answer. The result on the screen looks ordinary. The route to it was not. This is one of the quietest shocks in modern physics. The final evidence of a quantum process often arrives as something completely classical. A dot, a click, a voltage, a number. The strangeness is not always in the final mark. It is in the pattern that many marks form, or in the task that the device performs faster than expected, or in the correlations that cannot be explained by local classical pictures. The world speaks quantum through records that, once formed, look stubbornly definite. The same point returns us to ordinary experience with new precision. We do not live among visible superpositions because our world is saturated with records. The environment copies macroscopic information relentlessly. Our memories are built from physical traces in nervous tissue. Our instruments stabilize microscopic events into durable marks. Our shared reality depends on the fact that information, once amplified into the environment, becomes difficult to erase or recombine. But if fragile quantum behavior must be protected so carefully in a laboratory, then a new tension appears when we look outside the laboratory. Nature is not always warm chaos without structure. Living systems are noisy, but they are also organized. Molecules can be arranged with extraordinary precision. Energy can move through proteins on extremely short timescales. Chemical reactions can depend on electron spin, tunneling, and subtle quantum states. Evolution does not need to understand quantum mechanics in order to exploit physical effects that improve survival. This possibility must be approached carefully. Life is not magic, and biology does not suspend the rules that make decoherence so powerful. A cell is warm, wet, crowded, and full of motion. Those conditions usually destroy long-lived quantum coherence, but not every useful quantum effect requires a large, long-lived superposition. Sometimes the relevant process may be local, brief, and protected just enough by molecular structure to matter before noise takes over. The question then changes scale again. It is no longer whether a cat can remain in a dramatic macroscopic superposition. It is whether a protein, a pigment, an electron pair, or a molecular vibration can preserve a quantum relationship for a time short enough to survive and long enough to influence chemistry. In that form, the question becomes less sensational and more physically serious. It asks not whether life escapes decoherence, but whether life can use it, shape it, or outrun it in tiny windows of time. If a quantum computer needs cold metal, vacuum chambers, shielding, and careful pulses to protect coherence, what would it mean for a living system to borrow quantum delicacy inside heat, water, and noise? A leaf in darkness is not a passive surface waiting for sunrise. It looks still because its motion is too small and too fast for the eye to follow. Inside its cells, pigments are arranged with molecular care, held inside protein structures that do more than simply catch light. When a photon arrives, its energy does not always become heat immediately. It can lift an electron system into an excited state. And that excitation has to travel toward a reaction center before the energy is lost into the surrounding molecular noise. If energy moved through the leaf like an object stumbling randomly through a crowded room, much of it would be wasted. The interior of a living cell is warm, wet, and restless. Molecules twist, bonds vibrate, water shifts around proteins. Thermal motion constantly disturbs delicate relationships. These are exactly the conditions that, in a laboratory, would make physicists work hard to protect a fragile quantum state from decoherence. And yet photosynthetic systems can move energy with striking efficiency. That does not mean a plant is thinking. It does not mean life has escaped physics. It means that biological matter may sometimes arrange itself so that quantum effects survive just long enough to influence chemistry. The question is not whether a leaf becomes a quantum computer. The question is narrower and stronger. Can a living structure briefly use coherence before the surrounding warmth tears it apart? In some photosynthetic complexes, an absorbed photon creates an excitation that is not always best pictured as a tiny packet hopping along one fixed molecular route. Under certain descriptions, the excitation can be spread across several molecular states at once. Different possible transfer paths can contribute to the motion of energy. For a short time, the system may behave less like a bead moving along a track and more like a coordinated disturbance across a molecular network. The word coordinated is important. In this context, coherence means that parts of the quantum state maintain the phase relationships needed for interference. If those relationships persist, even briefly, the system's possible pathways can shape one another. Some routes may become less likely, others more favourable, not because the molecule chooses, but because the quantum amplitudes evolve under the structure of the protein and its environment. The surrounding vibrations are not merely background chaos. They may sometimes help guide the energy by matching the timescales of the transfer. This is where the simple picture of biological chemistry begins to bend. A living cell is not a quiet cryogenic device. It is not isolated behind polished shields. It is full of collisions and heat. Ordinary intuition says quantum coherence should vanish almost instantly in such conditions. If that were always the whole story, then any quantum relationship in a biological complex would be destroyed before it could matter. Energy transfer would reduce to a classical random walk through molecular disorder. The evidence is more careful than the most dramatic claims. Researchers have observed signatures in some photosynthetic systems that have been interpreted as coherence-like behaviour on very short timescales. There is debate over exactly how much of this behaviour is truly quantum electronic coherence, how much comes from vibrational motion, and how directly it contributes to biological efficiency. But the narrow possibility is enough to sharpen the problem. Life may not need long-lived quantum delicacy. It may need only a small interval in which structure, vibration, and excitation move together before noise closes the window. A protein is not just a scaffold. It shapes the energy landscape through which an excitation travels. The distances between pigments matter, their orientations matter, their energy levels matter. The surrounding protein can shift those levels slightly, creating pathways that are neither completely rigid nor completely random. If an excitation begins spread over more than one pigment state, then the molecular environment can determine whether that spread is useful or quickly lost. This creates an unusual kind of partnership between order and noise. In a simple engineering mindset, noise is always the enemy. In photosynthetic energy transfer, too much noise destroys coherence, but too little coupling may trap energy, or prevent it from reaching the reaction center efficiently. Some models suggest that a moderate amount of environmental interaction can help energy escape local traps, guiding it through the network rather than freezing it in place. The living system does not defeat decoherence by eliminating the environment. It may work near a boundary where environmental motion damages and assists at the same time. That boundary is more interesting than a miracle. It does not require a plant to preserve a grand quantum superposition across the whole leaf. It only asks whether specific molecular excitations, on very short timescales and within protected structures, can retain enough quantum character to influence the route of energy. The scale is tiny, the duration is brief, the physical consequence is real. A photon's energy must reach the place where chemistry can store it, or it will be lost as heat. The same caution changes how quantum biology should be heard. It is not a license to call every living process quantum in a vague sense. All matter obeys quantum mechanics at base, but that statement alone explains almost nothing. The useful question is whether a specifically non-classical effect changes the function of a biological process in a measurable way. If the answer is yes, then the mechanism must be identified. If the answer is uncertain, the uncertainty belongs inside the science, not outside its decoration. Photosynthesis offers one version of the question: how does energy move? Enzymes offer another: how does a reaction cross a barrier? In classical chemistry, molecules react when their atoms rearrange by passing over an energy barrier. Heat, molecular collisions, and the shape of the enzyme help make that crossing possible. But quantum mechanics allows a different kind of passage. A particle can sometimes tunnel through a barrier that it could not climb over in the classical picture. Tunneling is not a metaphor for persistence. It is a mathematical and physical effect. A particle described by a wave function can have a non-zero probability of appearing on the other side of a barrier, even when classical energy accounting would forbid the crossing. The probability usually falls rapidly with barrier width and particle mass. Electrons tunnel far more readily than heavier atoms. Protons can tunnel in certain conditions. Larger objects do not tunnel through everyday barriers in any useful sense, because the probabilities become fantastically small and decoherence overwhelms the effect. Inside enzymes, distances are molecular, and some transferred particles are light enough for tunneling to matter. An enzyme can hold reacting groups in a geometry that narrows a barrier, aligns donor and acceptor, and changes the local energy landscape. It may not simply push the reaction over a hill. It may create conditions where quantum tunneling contributes to the rate. The enzyme's structure, vibrations, and thermal motions can influence how often that tunneling happens. This does not make enzymes conscious machines. It makes them physical structures shaped by evolution. If a certain arrangement speeds a reaction, organisms carrying that arrangement may gain an advantage. Over generations, proteins can become exquisitely tuned to chemical tasks without any foresight. A molecule has no intention. A protein does not plan. But selection can preserve structures that exploit the available laws of physics, including laws that are quantum at the scale of electrons and protons. The consequence is quiet but deep. Life is often described as chemistry, and that is true, but chemistry is already quantum mechanics organized into bonds, orbitals, energy levels, and reaction pathways. The real question is not whether biology is quantum at the deepest level. It is whether biology sometimes depends on quantum effects that remain visible at the level of function. Does tunneling change reaction rates enough to matter? Does coherence shape energy flow enough to matter? Does spin dynamics help an animal sense a field too weak to feel as a mechanical force? That last question leads away from leaves and enzymes into migration. Many birds navigate over enormous distances, and the Earth's magnetic field appears to play a role in their orientation. But the planet's magnetic field is weak. It does not pull a bird north like a magnet pulling iron filings across a desk. Biological tissue is warm and noisy. A direct mechanical effect on ordinary molecules would be far too small to explain a reliable compass by itself. If a living sensor can detect that field, it needs a mechanism sensitive to something more subtle than a simple tug. One important hypothesis involves radical pairs. A radical pair is a pair of molecular fragments with unpaired electrons. Electrons have spin, a quantum property that behaves in some ways like an internal angular momentum, though it is not literally a tiny rotating ball. When a radical pair is created, the spins of the two unpaired electrons can be correlated. Their joint spin state can influence which chemical products form when the pair recombines or reacts further. A magnetic field can affect the spin evolution of such a pair. The field does not steer the bird's body. It changes the relative probabilities of chemical outcomes by influencing the quantum spin dynamics inside a molecule. If those chemical outcomes feed into a biological signal, then the animal may receive directional information. The compass would not be a tiny needle. It would be chemistry whose probabilities depend on orientation. This is a precise kind of strangeness. A field too weak to shove tissue around may still alter the fate of a short-lived quantum state. The effect has to survive long enough to influence chemistry. It has to be connected to sensory pathways, It has to operate in the noisy conditions of a living organism, and it has to produce a signal reliable enough to help guide behaviour. None of those steps can be assumed. Each one is a physical demand. The radical pair idea remains an active area of research, not a finished explanation for every detail of animal navigation. Candidate molecules, such as cryptochromes in the eye, have been studied because light-activated chemistry can create radical pairs under biological conditions. Experiments and models support the plausibility of spin-dependent chemistry in some systems, but the full pathway from molecular spin dynamics to animal orientation is still difficult to pin down. The careful claim is not that the bird sees alternate worlds. It is that a biological compass may depend on quantum spin chemistry. Even in that careful form, the idea changes the texture of the problem. The Earth's magnetic field is large in planetary extent but tiny in molecular energy. Thermal motion inside a cell is much stronger in many ordinary ways. A signal should disappear into noise unless the organism uses a mechanism that translates the weak field into a chemical difference before random motion washes it away. Radical pairs offer one possible translation. They turn direction into probability. They turn a barely felt field into a bias in reaction products. There is a kind of discipline in this. Good quantum biology does not begin with the word quantum and then search for wonder. It begins with a biological function that is hard to explain classically at the relevant scale. Energy moves too efficiently for a crude random model. A reaction proceeds with isotope effects suggesting tunneling may contribute. An animal responds to a weak magnetic field that should be difficult for warm tissue to detect. Then the question becomes mechanistic. What physical process could carry the signal? This is also why many claims must be rejected or left outside the main path. Saying that life is mysterious is not enough. Saying that the brain is complicated is not enough. Saying that quantum mechanics is strange is not enough. A useful claim must identify the system, the state, the timescale, the interaction, and the measurable consequence. Without that, the language becomes fog. With it, even a modest effect becomes powerful. The strictness matters most when the discussion approaches the brain. The brain is the most tempting place to overreach because experience feels private, vivid, and difficult to reduce to chemistry. A thought does not feel like ions moving across membranes. A memory does not feel like synaptic change. A dream does not feel like a network generating images without external input. Because the inner world feels so unlike a machine. It is easy to pull quantum mechanics into the gap and ask it to do more than the evidence allows. The brain is certainly physical. Neurons use voltage differences, ion channels, neurotransmitters, receptors, molecular signaling pathways, metabolic energy, and changing synaptic strengths. At small scales, all of these depend ultimately on quantum chemistry. Bonds form because electrons occupy quantum states. Molecules absorb and emit energy according to quantum rules. Proteins change shape according to forces rooted in atomic interactions. In that broad sense, the brain cannot be outside quantum mechanics. But the stronger claim is different. It says that specifically quantum coherence, entanglement, or measurement-like effects play a direct functional role in consciousness or thought at the cognitive level. That claim is far less established. The brain is warm, wet, and strongly coupled to its environment. Neuronal firing occurs over timescales much slower than many delicate quantum processes. The activity that supports perception and memory appears, in current neuroscience, to be well described largely through classical and biochemical dynamics at the level of cells and circuits, even though those dynamics rest on quantum chemistry underneath. This does not make consciousness easy, it only prevents a shortcut. The difficulty of explaining subjective experience does not automatically point to quantum coherence as the missing mechanism. A gap in one science is not evidence for an unproven claim in another. If quantum processes matter in consciousness in a special way, they would need to be shown through mechanisms that survive decoherence, produce measurable neural effects, and explain something that ordinary neurobiology cannot. That standard is demanding, and it should be. The history of quantum mechanics has already shown that the word observer can mislead. In measurement theory, an observer does not have to be a conscious mind. A detector or environment can play the relevant physical role. If that point is forgotten, the brain becomes falsely promoted from participant in nature to controller of nature. The science does not support that jump. Still, the brain remains relevant for a quieter reason. It is not needed to collapse a wave function, but it is needed for experience. A detector can record a result without knowing it. A notebook can contain a number without understanding it. A memory, however, gives the result a place inside a lived sequence. When a person sees a detector reading, the physical record enters a neural model of the world. The world becomes not only measured, but perceived. Perception is not a passive copy. The brain constantly builds a working model from sensory input, expectation, memory, body signals, and correction from the environment. Vision, for example, is not a simple projection of the outside world onto awareness. Light strikes the retina. Signals are processed through multiple neural layers. Features are extracted. Motion is estimated. Contrast is enhanced. Predictions are updated. What feels immediate is the result of active construction. This construction is not arbitrary. During waking life, the model is constrained by incoming data. If you misjudge the location of a cup, your hand misses it. If the floor slopes unexpectedly, your balance system corrects. If a sound comes from behind, you turn and test the prediction. The environment pushes back. Other people can confirm or contradict what you report. Instruments can stabilize perception into shared measurement. Waking reality feels solid, partly because the model is constantly being disciplined by the world. Dreaming loosens that discipline. During sleep, the brain can generate scenes without the same level of external sensory correction. A corridor may bend into a childhood street. A person may appear with no coherent history. Time may jump without warning. Yet inside the dream, the scene can feel real enough to produce fear, relief, urgency, or recognition. The brain is not receiving a normal world through the senses, but it is still capable of building a world-like experience. This is why dreams become tempting in discussions of parallel possibilities. They feel like visits to other versions of events. You wake with fragments that do not fit the day you lived. A conversation happens that never happened. A room exists that seems familiar only while you're inside it. The feeling can be intense, and the mind naturally asks whether some deeper physical place has been touched. That step goes too far scientifically. There is no established mechanism showing that dreams communicate with other branches of a many-worlds quantum state. Decoherence, if anything, makes such communication inaccessible in the usual picture. Branches that have become effectively independent do not provide a channel for dream imagery to cross back into waking memory. The more careful view is not as sensational, but it is still important. Dreams show how convincing a constructed reality can become when the brain generates a world from within. That lesson fits the central problem without abusing it. Quantum mechanics asks how a world of definite records emerges from a deeper description, involving amplitudes, interactions, and measurement. Neuroscience asks how a definite experience emerges from neural processing, prediction, memory, and sensory correction. These are not the same problem, and they should not be collapsed into one. But they touch at the place where physical records become lived reality. A measurement in a lab becomes part of someone's world only when a brain incorporates it into perception and memory. The distinction between record and experience is subtle. A detector's mark can exist without being seen. A buried fossil can preserve an event for millions of years before any organism interprets it. A computer drive can store data no person has read. Physical records do not require consciousness. But conscious life is one way records become meaningful to an organism. It turns signals into surroundings, surroundings into choices, and choices into memory. This is why the feeling of one world is not explained by quantum physics alone. It also depends on how living brains bind information. At any moment, the nervous system integrates many signals into one usable scene: vision, balance, touch, body position, sound, internal state, expectation. If those signals failed to bind, experience would fragment. If memory failed to order events, the self would lose continuity. The one world we experience is not only a quantum classical outcome, it is also a biological achievement. The achievement is fragile in its own way. Illusions show that perception can be wrong while feeling certain. Dreams show that certainty can arise with little external input. Neurological disorders can split attention, distort body ownership, disrupt memory, or alter the sense of agency. These facts do not make reality unreal. They show that access to reality is mediated by a physical system with its own rules and limits. The connection to quantum measurement should therefore be made carefully. Quantum theory does not say that subjective certainty creates the external world. It says that microscopic systems are described by states whose possible outcomes become definite records through physical interaction, at least in the operational description. Neuroscience says that the brain constructs experience from signals and internal models. When the two are confused, the result becomes pseudoscience. When they are kept distinct, they reveal a more disciplined picture. The world is measured physically and then modelled biologically. A sleeping brain is a useful contrast because it preserves the modelling while loosening the measurement. During a dream, there may be vivid objects, but they are not anchored to external records in the same way waking objects are. A dream door can change because no shared environment forces it to remain stable. A dream message can appear without a phone receiving a signal. A dream room can vanish without leaving debris. The internal model has coherence enough for experience, but not the public durability of waking facts. Waking experience is different because it is locked to records outside the brain. Light reflected from objects constrains vision. Sound waves constrain hearing. Touch constrains body position. Other observers constrain reports. Instruments constrain guesses. The world becomes shared because information about it is spread redundantly through the environment and through bodies that can compare their records. This is the physical basis for why science can work at all. It does not rely on private certainty. It relies on reproducible traces. The irony is that both quantum physics and dreaming teach distrust of naive immediacy, but in opposite directions. Quantum physics says the microscopic world may not possess all ordinary properties before measurement in the classical way we expect. Dreaming says the brain can generate a strong sense of reality without the usual external anchor. One challenges the object before it becomes a record. The other challenges the subject after a world has been modelled. Between them sits the fragile bridge of measurement, memory, and interpretation. This bridge is not mystical. It is made of physical events. Photons scatter from a surface. A retina absorbs them. Neurons fire. Synapses change. A memory trace becomes more likely to reactivate. A person later says, "I saw this." The statement may be checked against other records. The chain begins outside the body and ends inside a model, but no link requires a supernatural addition. The difficulty lies in the complexity of the chain, not in a license to abandon mechanism. The same discipline applies to decisions. Human choice feels like a branching of possibilities. A person can answer a message or leave it unread, turn left or right, speak or remain silent. Because quantum theory also contains alternatives, it is tempting to merge these two kinds of branching. But ordinary decision-making is a high-level biological process involving neural dynamics, memory, emotion, sensory input, social context, and bodily state. It should not be casually identified with quantum branching. Some microscopic quantum events may influence biological processes in principle. A molecular event can be amplified. Thermal fluctuations can affect neural timing. Randomness can enter complex systems. But the existence of microscopic uncertainty does not mean every thought is a clean quantum measurement, with a set of separate worlds corresponding to each imagined option. The brain is not an isolated array of qubits. It is a warm organ whose activity is strongly coupled to its own environment. This makes the human sense of possibility both real and different from quantum superposition. Before you make a decision, several futures may be open in a practical sense because your brain has not yet settled into one action. But those futures are not necessarily coherent quantum alternatives capable of interference. They are possibilities in a biological, informational, and behavioural sense. They matter deeply for life. But they should not be mistaken for the same object described by the wave function of a controlled quantum system. The difference does not reduce their importance. A life is built from these practical branch points. Bodies move through environments, learn from consequences, and stabilize patterns of behavior. Memory turns actions into a personal past. Anticipation turns uncertainty into planning. The fact that this is not the same as a quantum superposition does not make it less physical. It only places it at the correct level of description. Levels of description are not excuses, they are necessities. A protein can be described by quantum chemistry, but a cell cannot be usefully understood by writing the wave function of every particle. A brain can be described by atoms, but thought requires higher-level patterns of neural activity. A detector can be described by quantum fields, but its reading can be treated as classical once decoherence has stabilized the record. Good science moves between levels without pretending one level erases the others. The danger comes from choosing the most mysterious level and using it to explain everything. Quantum mechanics is deep, but not every unexplained experience becomes quantum by default. Consciousness is difficult, but difficulty is not evidence for a specific physical mechanism. Many worlds is intellectually striking, but it does not turn dreams into messages from alternate branches. Decoherence is powerful, but it does not by itself solve every question about subjective experience. What it does offer is a sharper map of the boundary. On one side are controlled quantum systems, where coherence can survive and interference can be measured. On another are ordinary macroscopic records, where information has spread too widely for interference to be recovered. In living matter, there may be small pockets where quantum effects influence function before decoherence wins. In the brain, current evidence supports quantum chemistry as the foundation. While stronger claims about long-lived coherent quantum consciousness remain unproven. The map is not flat, it has narrow passes. Photosynthetic complexes may briefly guide excitation through structured molecular networks. Enzymes may use tunneling to alter reaction rates. Radical pairs may let weak magnetic fields bias chemical outcomes. These are not portals out of physics. They are places where physics is more finely tuned than the everyday picture suggests. At each pass, the same question repeats with a different object. How long can coherence last? What information leaks into the environment? Does the effect change a measurable outcome? Can the system use the effect before noise erases it? The answer may be yes in one molecular setting, no in another, uncertain in a third. The value of quantum biology lies precisely in refusing a single easy answer. This refusal creates a more mature kind of wonder. A plant does not need awareness to move energy with molecular skill. A bird does not need to feel a magnetic field as a force if chemistry can translate orientation into reaction yield. An enzyme does not need intention to make tunneling useful. Life can exploit mechanisms without representing them. It can build delicate functions out of laws it does not know. That is how evolution often works. It does not design from theory. It filters variations through consequences. If a molecular arrangement transfers energy more reliably, it can be favoured. If a sensory mechanism helps orientation, it can be preserved. If an enzyme lowers an effective barrier, metabolism can run more efficiently. Physics supplies the possible moves. Evolution tests which moves matter inside bodies. The result is neither magical nor mechanical in the crude sense. It is layered. Quantum rules shape molecules. Molecules shape cells. Cells shape organisms. Organisms build nervous systems. Nervous systems build models. Models produce the feeling of a world. At no point does the chain become less physical, but at each level new descriptions become necessary because the patterns grow more complex. This layered view also changes the emotional weight of the original question. The world becomes one for us not through a single act, but through many stabilizing processes. Decoherence suppresses interference between macroscopic alternatives. Environmental records make facts public. Biological senses sample those records. Brains bind them into scenes. Memory threads scenes into a past. What feels like one continuous reality is supported by an enormous amount of physical and biological coordination. If any layer failed, the one-world feeling would weaken. Without decoherence, macroscopic records would not behave with ordinary stability. Without environmental copying, facts would not become shared. Without sensory correction, perception would drift. Without memory, experience would not accumulate into a personal history. The solidity of waking life is therefore not a simple given. It is a maintained condition. Dreams reveal what happens when part of that maintenance is relaxed. The brain still makes scenes, but the outside world no longer corrects them in the usual way. The model can become fluid while remaining convincing. A dreamed staircase can lead to a room that could not fit inside the house. A person can be both familiar and impossible. Time can fold without resistance. The mind accepts the scene because the systems that test and update waking reality are operating differently. This does not make dreams less meaningful psychologically, it makes them poor evidence physically. They may reveal memory, emotion, prediction, fear, desire, and the brain's ability to simulate. They do not, on current evidence, reveal a channel to other quantum branches. That distinction protects both sides. Dreams can be fascinating without being misused as proof. Quantum mechanics can be strange without being stretched into a theory of every inner image. The better connection is this. Both dreaming and quantum measurement show that what is real to an observer is not a simple phrase. In physics, an observer is part of an interaction chain that produces records. In neuroscience, an observer is a living model builder whose experience depends on how signals are integrated. The same word points to two different mechanisms. Confusing them creates false drama. Separating them reveals why reality can be both physically stable and subjectively constructed. A detector does not dream. A brain does not merely detect. Between them lies the difference between record and world. A record is a physical correlation. A world is a structured field of experience, built from records, body states, memory, and expectation. Science can study both, but it cannot replace one with the other by changing vocabulary. The detector's click is not yet a human reality. The dream's corridor is not yet an external fact. Somewhere in that difference, the old unease returns in a new form. The quantum world asks why measurements have definite outcomes. The biological world asks how definite outcomes become a lived scene. The dream world asks why a scene can feel definite even when it is poorly anchored to external records. Each question removes a different kind of simplicity. Together, they show that the single world we inhabit is not a plain surface. It is a convergence. The convergence begins before perception. A measurement apparatus interacts with a system. Information spreads into the environment. Macroscopic alternatives stop interfering for all practical purposes. Then, a body samples the environment through senses. The brain binds the sampled information into a model. The model becomes the world the organism can act within. By the time awareness says, "This is happening," many layers of selection, stabilization, and construction have already occurred. The phrase, "this is happening," feels immediate. It rarely feels like the end of a chain. But it is the end of many chains at once: optical, neural, thermal, chemical, environmental, historical. The lamp is lit because an electrical circuit changed state. The room is visible because photons scatter. The eye responds because molecules in the retina change shape. The brain interprets because networks have been trained by a lifetime of correction. The memory persists because physical structures are altered. This is why the deepest question cannot be solved by choosing only physics or only perception. A world without stable physical records would not support shared experience. A brain without modelling would not turn records into a lived environment. A theory of branching without decoherence would not explain why branches fail to interfere. A theory of consciousness without biology would float away from the body that makes experience possible. The one world we know sits at the intersection of all these constraints. But the intersection is not the final answer. It is the place where the answer becomes more difficult. If physical reality is described at the deepest level by a quantum state, and if experienced reality is built by brains from records, then the world is not a single simple thing. It is at least two descriptions meeting: the external structure that produces stable records, and the internal model that turns those records into a lived present. Neither description can safely replace the other. The external structure prevents dreams from becoming evidence of alternate branches. The internal model prevents measurement records from explaining experience by themselves. Between them is the exact place where exaggeration is easiest and precision is most necessary. A bird crossing a dark sky may be guided by chemistry sensitive to a weak magnetic field. A leaf may move sunlight through molecular states before heat can scatter the order. A sleeping mind may build a city from memory and expectation, then wake with the feeling of having been somewhere else. None of these requires a violation of physics. Each shows, in a different way, how delicate the line can be between signal and noise, record and model, possibility and fact. The central question has not disappeared. It has become more demanding. Quantum mechanics explains why possibilities cannot always be treated as ordinary ignorance. Decoherence explains why macroscopic alternatives become effectively separate or inaccessible. Biology shows that living systems may sometimes operate close to the edge where quantum effects still matter. Neuroscience shows that the experienced world is actively constructed from physical signals. The single line of experience is not given for free, it is assembled and stabilized. And once that is understood, the word world begins to carry more weight. It can mean the total physical state if such a description is meaningful. It can mean one decohered branch, in interpretations where branches are taken seriously. It can mean the public environment of shared records. It can mean the private model inside a brain. In ordinary speech, these meanings overlap so smoothly that we do not notice the seams. In science, the seams matter. The next difficulty is that some of those meanings may not be directly testable in the same way. A detector pattern can be measured, a molecular reaction can be timed, a neural signal can be recorded, but an entire branch of the universal wave function, if it no longer interferes with ours, may not offer the same kind of access. The interpretation may explain the mathematics elegantly, while remaining difficult to distinguish experimentally from other interpretations. That is not a reason to dismiss the question, it is a reason to ask it with care. Physics often advances by separating what can be measured now, what can be modelled, and what belongs to interpretation. The danger is not asking too much, the danger is forgetting which layer one is standing on. If dreams are not windows into other branches, and if consciousness does not collapse reality by command, then what exactly makes one experienced world feel so complete, while the deeper theory still speaks in amplitudes? Memory feels like a return, a sound, a smell, a certain angle of evening light, and the mind seems to step backward into a place that has been waiting unchanged. The past feels stored somewhere behind the present, fixed and silent, ready to be opened again. But the brain does not preserve experience like a sealed photograph protected from time. Remembering is an active physical process, and every act of recall can slightly rebuild what it retrieves. That does not mean memory is false, it means memory is biological. A remembered event depends on traces distributed through neural systems, strengthened connections, patterns of reactivation, emotional weight, sensory fragments, language, and the later meanings attached to what happened. When a memory is recalled, it can become flexible for a time before being stabilized again. Details may sharpen, fade, merge, or shift. The result can still point toward a real event, but it is not the event itself preserved without alteration. This difference matters because it is easy to confuse psychological uncertainty with quantum uncertainty. If someone cannot clearly remember what they said 10 years ago, that does not mean the past is in a quantum superposition, waiting to be measured. It may mean the memory trace is weak, reconstructed, contaminated by later knowledge, or reshaped by emotion. The uncertainty belongs to the brain's record, not necessarily to the physical event itself. Quantum uncertainty is different. It has a mathematical structure. It appears in interference, amplitudes, measurement statistics, and the limits of what can be assigned to a system before measurement. A blurred memory is not the same kind of object as a wave function. One is a biological reconstruction. The other is a physical state description used by quantum theory. Confusing them makes both less clear. And yet the comparison is not useless if it is kept in its proper place. Both memory and quantum measurement challenge the naive idea that reality is always just a collection of finished facts waiting passively to be found. In the microscopic world, certain properties are not always best treated as pre-written classical values. In the brain, the past is not always accessed as an unchanged recording. In both cases, the simple picture of discovery gives way to a more active process: preparation, interaction, trace, reconstruction, record. The difference is that quantum mechanics concerns what can be physically measured in microscopic systems, while memory concerns how a nervous system preserves and rebuilds information. One is not a metaphorical version of the other, but they meet in lived experience because the world we know is built from records, and memory is the record that gives a life its line. A person does not merely receive events, the person carries them forward. A word spoken in anger may exist first as vibration in air, then as neural activity in another body, then as a remembered wound, then as a change in future behaviour. A kindness may leave no mark on stone or metal, yet still alter the pattern of someone's choices. In that sense, the past is not only what happened, it is what remains physically able to influence the present. This is not mystical, it is how records work. Information matters only when it is embodied in a state that can make a difference later. A detector record matters because it changes a device. A photograph matters because light altered a sensor or a chemical surface. A memory matters because the brain is physically changed in a way that can be reactivated. Information is not a floating substance. It is a difference held somewhere. At the quantum level, this becomes especially sharp. If a detector records which path a particle took, interference is lost. If the environment carries away information about a system's state, coherence becomes inaccessible for practical purposes. If a measurement outcome is amplified into a durable mark, the world gains a record that can be shared. Information is not only something we learn afterward. In physical systems, the availability of information can change what patterns are possible. This gives time a particular texture. In ordinary experience, the past is fixed and the future is open. We remember behind us and anticipate ahead of us. But in physics, the distinction is not simply a line drawn by feeling. The past is full of records. The future is not. Broken shells on a beach, tree rings, craters, fossils, burned fuel, stored data, changed synapses, scattered photons moving away into space. These are physical asymmetries. They make the past available in a way the future is not. Quantum measurement fits into that asymmetry. Before a measurement, the theory may assign amplitudes to several possible outcomes. Afterward, there is a record. The record does not have to be read by a person to become part of the physical world. It may be embedded in a detector, an environment, or a chain of correlations too complex to reverse. The transition from possibility to recorded outcome is therefore tied to the same broad direction that gives the past its weight. Information spreads. And the spreading is difficult to undo. This does not mean time itself has been fully explained. The arrow of time involves thermodynamics, entropy, boundary conditions of the universe, and questions that reach far beyond any single experiment. But the measurement problem shows one place where the arrow becomes concrete. A fragile quantum relationship can be protected, recombined, and made to interfere only while the relevant information has not escaped. Once the information has spread widely enough, reversing the process would require impossible control over countless degrees of freedom. The irreversibility is often practical rather than absolute. In the full equations, many microscopic processes can be reversible in principle, but principle is not always power. A drop of ink dispersing in water follows molecular laws, yet gathering every molecule back into the original drop would require knowledge and control far beyond any realistic device. In the same spirit, a quantum system entangled with a vast environment may still be described by reversible mathematics at the largest scale, while interference between its macroscopic alternatives is unreachable for any practical observer inside that world. This practical irreversibility is one reason our lives feel continuous. We move through a world in which records accumulate, Footsteps disturb dust. Light leaves images. Bodies age. Brains update. Heat diffuses. Events do not usually unwrite themselves. A cup that shatters does not reassemble, because the information and energy involved in the shattering have spread into sound, heat, motion, and microscopic disorder. The past becomes heavy because it has many traces. From here, the idea of choice takes on a more careful shape. Human life is full of branch points, a message answered or ignored, a hand extended or withheld, a road taken because the weather changed, a sentence spoken before it could be softened. These moments feel like openings, and in the human sense they are. The brain considers possible actions, predicts consequences, draws on memory, emotion, habit, values, and bodily state. Then one action becomes real enough to enter the world. It is tempting to attach this directly to quantum branching. But ordinary decisions should not be casually treated as clean quantum measurements. A human choice is a large biological process, spread across neural circuits and embedded in a body and environment. It may contain microscopic noise and physical uncertainty, but the meaningful structure of a decision is not mere randomness. A random twitch is not freedom. A quantum fluctuation by itself is not responsibility. Responsibility grows from organization. A person can remember, evaluate, inhibit, imagine, learn, regret, repair, and choose differently next time. These capacities require stable records inside the brain and body. They require a model of the world, not just an opening in causality. If every action were only a dice throw, it would not become more personal. It would become less connected to the person. So quantum mechanics does not prove free will, and it does not erase it. It shows that the old picture of the universe as a simple clockwork machine was incomplete at microscopic scales. But the space between clockwork and chaos is wide. Inside that space are complex systems, feedback loops, memory, biological regulation, prediction, learning, social meaning, and conscious deliberation. A human being is not an isolated particle choosing a path through two slits. A human being is a living structure that turns many kinds of information into action. This does not drain the feeling of choice, it grounds it. The importance of an action does not come from proving that all alternatives physically continue somewhere else. It comes from the fact that this organism, in this environment, with this memory and this body, produces one trace in the shared world. The action becomes part of other people's records. It changes conditions. It can heal, damage, open, close, teach, or remain hidden while still shaping what comes later. If many worlds is taken seriously as an interpretation, then there may be a wider description in which multiple outcomes continue in different branches. But even there, responsibility does not dissolve. An observer inside a branch does not stand above all branches like a detached equation. They live within one history with one body, one set of memories, and one network of consequences. The branch they inhabit is not made less real to them because a theory describes a larger structure beyond it. That is one of the reasons the many worlds image must be handled with restraint. It can widen the imagination, but it can also flatten life if misunderstood. The thought that other outcomes might exist somewhere does not make this outcome meaningless. In fact, it can do the opposite. It can make the experienced line feel more fragile, because it is the only line available to the person living it. Physics may describe possibilities. Life is lived through records. At night, this difference becomes less abstract. The mind returns to small moments that could have gone another way. A phone call answered after hesitation. A door closed too hard. A word kept back until it was too late. A choice that seemed minor at the time then became part of a longer pattern. These are not laboratory superpositions. They are the human form of possibility. Imagined futures narrowed into acts, acts hardened into memory, memory shaping what can happen next. The same movement can be seen at larger scales. A star forms from a collapsing cloud because gravity overcomes pressure in one region of gas. A planet keeps or loses an atmosphere depending on mass, temperature, radiation, magnetic environment, and time. A galaxy records its past in the motion and chemistry of its stars. The universe we observe is full of traces. It is not only a collection of objects, it is a vast archive of interactions. On cosmic scales, quantum mechanics does not disappear. The atoms in stars, the spectra of elements, the behaviour of light, the stability of matter, the nuclear reactions that make heavier elements, all of these depend on quantum rules. The large universe appears classical, not because the quantum layer is absent, but because decoherence and scale make most macroscopic alternatives non-interfering in practice. Stars shine through quantum processes, yet their positions in the night sky do not behave like visible double-slit patterns. Looking upward can make the question feel too large. Galaxies seem steady. Time seems immense. The human observer seems almost too small to matter, but the same logical structure remains. At one scale, amplitudes define probabilities. At another, records accumulate. At another, living systems read some of those records and build worlds from them. The apparent solidity of the sky and the apparent solidity of a room are both supported by layers of interaction that suppress the delicate features visible only under special conditions. If there is a universal wave function, as some interpretations propose, then our whole observable world may be one part of a much larger quantum description. But this is not a directly photographed object. It is a way of reading the formalism. The idea is serious but not simple. It raises questions about probability, branching, identity, and what it means for something to be physically real if it cannot interact with us after decoherence. These questions are not solved by giving them dramatic names. Science advances by separating what is measured from what is inferred, and what is inferred from what is imagined. We measure detector clicks, interference patterns, spectra, decay rates, coherence times, chemical outcomes, neural activity, and cosmic light. We infer states, amplitudes, histories, models, and mechanisms. We imagine metaphors to hold what the equations and observations do not easily fit into ordinary language. Problems begin when the metaphor is mistaken for the measurement. The many worlds interpretation, collapse theories, relational approaches, pilot wave theories, and other interpretations each attempt to explain or reframe the quantum formalism. They do not all tell the same story. Some keep only one outcome by adding or emphasizing collapse. Some keep all outcomes in a broader state. Some shift attention to relationships between systems. Some restore hidden variables in a non-classical way. The fact that these interpretations exist does not mean physics is lost. It means the operational theory is stronger than our agreement about its image. That difference is rare but not shameful. Quantum mechanics tells physicists how to calculate with astonishing precision. It predicts the behavior of atoms, light, semiconductors, lasers, superconductors, and many delicate laboratory systems. The disagreement lives in what the successful calculation says about reality between preparation and measurement. If the theory failed, the mystery could be dismissed. Because it works, the mystery has to be treated with respect. This is the controlled humility at the centre of modern physics. Nature does not owe us a picture that fits into the habits of a primate nervous system. The equations may be precise while the imagery remains incomplete. A particle may not be a tiny bead. A wave function may not be a water wave. A measurement may not be a human look. A world may not be one simple object described the same way at every level. Still, science is not helpless. It builds better language by forcing ideas through experiment. Interference is not vague because it leaves patterns. Decoherence is not vague because it changes how systems lose phase relationships. Quantum computation is not vague because devices either preserve coherence long enough or they fail. Quantum biology is not vague when it asks about specific molecules, timescales, and reaction outcomes. The discipline is what keeps the strangeness honest. The word law also changes under this pressure. A law of nature is not always a script that writes every individual event as a visible sentence in advance. In quantum mechanics, a law can be a rule for the evolution of states and the probabilities of possible measurement outcomes. It may not determine where one electron lands in a single trial, but it determines the statistical pattern with great precision. Randomness here is not lawlessness, it is structured. This structured uncertainty is very different from everyday confusion. If you do not know whether a letter is in a drawer, the letter still has a location. If a quantum system is in a superposition, the state may not assign a single classical value to the property being measured. That is why the double-slit experiment cannot be reduced to ignorance about a path. The final pattern depends on interference between amplitudes. The uncertainty has teeth. Information gives those teeth a boundary. When path information exists, the interference changes. When environmental information spreads, decoherence follows. When a result is amplified into a record, the world becomes classical for the observers tied to that record. The story is not that consciousness chooses reality. The story is that information, physically embodied, changes what kinds of interference remain available. This is why the ordinary room at the beginning was never truly ordinary. The glass, the phone, the light switch, the walls, the air, each object is constantly involved in interactions that make its state available to the environment. Photons scatter from surfaces, molecules collide, heat flows, materials vibrate. The world is being recorded from every direction, not by a single observer, but by its own internal traffic of matter and energy. That recording is what lets different observers agree. A person can leave the room, and another can enter and find the glass still there because its position was never only private. It was supported by a dense web of correlations. Reflected light, contact with the surface beneath it, gravitational support, air currents disturbed around it, thermal radiation exchange with the room. The glass is not definite because someone continuously thinks about it. It is definite for all practical purposes because the environment has made alternatives involving very different positions, unable to interfere in any accessible way. At the human scale, this is a gift. It gives us reliable objects, durable tools, shared places, and memories that can be checked. A world where macroscopic alternatives freely interfered would not support ordinary life. Instruments could not hold readings. Bodies could not maintain stable boundaries. Communication would lose its anchor. Science itself depends on the classical reliability that quantum theory must explain. At the microscopic scale, the same reliability becomes a loss. Once a system is recorded too strongly, the delicate interference vanishes. The quantum experimenter must protect the system from becoming too much like the everyday world. Isolation, cooling, shielding, timing, and error correction are methods of delaying ordinary definiteness. They create a pocket where possibility remains physically useful before it's converted into fact. The whole story can be heard as a tension between privacy and publicity. A coherent quantum state is private in a physical sense. Its alternatives have not yet been widely copied into the environment. They can still interfere. A classical fact is public. It has left traces. It can be read by many systems. It is stable because it has been redundantly recorded. Measurement is the passage from one condition toward the other. Living systems occupy the passage in more complicated ways. They are not isolated quantum devices, but they are not featureless classical machines either. Their molecules are arranged with precision. Their chemistry can exploit tunneling, spin dynamics, and perhaps short-lived coherence under specific conditions. Their brains build models from records and act before the future becomes a record. Life does not stand outside quantum mechanics. It organizes certain consequences of physics into survival. The brain then adds another layer. It does not create external measurement outcomes by thought alone, but it does create the experienced world from sensory evidence. It binds signals into scenes, scenes into memory, memory into identity. It can also dream, misremember, imagine, and anticipate. That is why the world we live in is both shared and personal. Shared because physical records constrain it. Personal because each brain builds its own model from those records. This dual structure explains why reality can feel absolute and still require care. The floor beneath the feet is not optional. The body cannot decide gravity away. A detector result cannot be changed by wishing. Yet the meaning of events, the continuity of memory, and the felt shape of the present are built by a nervous system. One layer keeps us honest. The other makes the world livable. The deepest question has therefore softened, but it has not vanished. We began with the mismatch between ordinary intuition and a detector pattern. A particle should have taken one path, yet the statistics carried the trace of multiple amplitudes. We followed the path information into measurement and saw that observation is not a magical gaze but a physical coupling. We watched that coupling scale upward into the problem of definite outcomes, then outward into interpretations where collapse may or may not be fundamental. We saw decoherence explain why fragile alternatives become inaccessible, and why the ordinary world feels so stubbornly single. We saw quantum computers use that fragility as a resource, and dreams remind us that the brain also builds worlds from signals, memory, and expectation. Nothing here proves that dreams cross universes, or that consciousness selects reality, or that every possibility is available to us. The more honest wonder is quieter. Reality is not simply what exists, and experience is not simply what is imagined. Between them lies the fragile work of records, bodies, memory, and measurement. Then the same tension entered technology, where quantum computers must preserve coherence long enough to make interference useful. It entered biology, where certain molecular systems may exploit quantum effects briefly before noise destroys them. It entered memory and perception, where the single world we experience is not a passive copy but a biologically constructed model, constrained by physical records. At every level the same pattern returned. Possibility becomes consequence only through mechanism. That is the quiet resolution available without pretending to know too much. The world we experience is not made simple because the underlying physics is simple. It becomes simple enough for life because interactions stabilize it. Information spreads. Records form. Coherence is lost where it cannot be protected. Brains bind what remains into a usable present. The single line of experience is not the denial of quantum possibility. It is what possibility looks like after it has passed through measurement, environment, body, and memory. There may be deeper truth still missing from this picture. Collapse may be real in a way not yet fully understood, or the wave function may never collapse, and our world may be one branch in a structure too large to picture. Or the right interpretation may require language that has not yet become natural to us. The current science does not force all physicists into one image. It does, however, force a more careful kind of wonder. The old everyday certainty was too simple. The wildest popular claims are too loose. Between them is a disciplined mystery, measurable, useful, unresolved. In that mystery, the ordinary world becomes more valuable, not less. The lamp, the glass, the quiet phone, the body in the room, the memory of choosing one action instead of another. None of these are trivial just because the deeper theory is strange. They are the stable surface produced by countless interactions, the level at which life can act, remember, and care. The world may begin in amplitudes we cannot picture easily, and it may contain possibilities our experience cannot follow. But here, in the record that holds, in the room that remains, in the one remembered path through time, reality becomes intimate enough to be lived.